Greetings everyone, this is Non-Expert here back again with another video. Today we are going to be solving problem number 29 of our 30 LeetCode challenge, and the problem that has been given to us today is the binary tree maximum path sum problem. If you want to try solving this problem on your own, you can pause this video and check out the LeetCode link given in the description below, and let's get started. So the problem description that has been given to us today is, given a non-empty binary tree, we need to find the maximum path sum. For this problem, a path is defined as any sequence of nodes from some starting node to any node in the tree along with the parent-child connection. The path must contain at least one node and does not need to go through a root. So the main essence of this problem is that we understand what the definition of a path is, and a path is any sequence of nodes which follow a parent-child connection relationship. So you've been given an example over here where you have 1, 2, 3 as the binary tree, and you can see that the thing which has been bolded is the actual maximum path sum, or the maximum path. So you have 2, 1, and 3, and when you sum them all up, the output becomes 6, and that's what you want to return. You've been given another example over here where you have minus 10, 9, 20, 15, and 17. And if you look at this thing, you don't really want to take minus 10 into account, because if you want to take 9 into account, you'll have to take minus 10 also into account, and that's just going to be negative 1 in total, so that's not going to be helpful. Rather, what you can do is you can take 15, 20, and 7, therefore the output becomes 42, and that's the maximum path sum. We do need to realize over here that if this minus 10 wasn't minus 10 and it was actually 10, well, in that case, the output would have to consider 10 and 9 as well. Therefore, the output in that case would not be 42, but rather it would have been 61. So before we start with the logic, we already know for a fact that this is a binary tree problem, and binary tree problems are usually solved using recursion. So that's something that we're going to be leveraging. That's point one. The second point that we need to be aware of is that we can actually use recursion to understand what's the maximum path sum that we've encountered on a left subtree and a right subtree. So if we have this node value over here, we can ideally using recursion, calculate what is the maximum path which has been encountered so far on my left subtree and what's the maximum path sum that we've encountered on our right subtree. And the last thing that we need to be focusing on is that the output is actually not the path, but rather the output, the maximum sum. So to get that, we're going to be using a global variable which we can reference as we're moving along. So let's just start with our implementation, and we always start with the base condition, so let's just do that. So if nothing has been given to us, we just return a simple 0. We're also going to be making a variable called self.max, which we can reference easily, and I'm going to give it a minus infinity value just so that, whatever next value that we get, it can be replaced with that. I like using a utility function just so that, inside the same function, that just makes it a lot more easier for me to code things out, but this is just my preference. So you could literally just, code out this entire solution using the max path sum. But I don't really prefer that, so I'm just going to use this utility function to traverse through all my elements inside my binary tree. And eventually what our expectation should be is that self.max is the value which is going to contain the maximum path sum that we found so far, and we basically return it. We are going to iterate, or rather not iterate, we're going to traverse through the binary tree using the utility function. So let's just go ahead and pass in the root, and let's just code in our logic for the utility function. So logic over here is pretty similar. We start with saying that if node is given as none, well, in that case you want to return a 0. For all other conditions, what we can do is we can basically, maintain a variable, call it as left, for basically getting the maximum um, path sum for the left subtree, and the same thing for the right subtree as well. So although we have not coded out the logic yet, I'm just assuming that left and right are going to contain the maximum subtree to whatever node that we're presently on. And after all these iterations happen, that's where our thing should actually, that's where our logic should fall into place. So in essence, to get the maximum left or right or whichever subtree it is, that's pretty straightforward. All we need to do is we need to return the maximum between the node.val versus the node.val plus maximum between left or right. So basically you're choosing either one. So if you look at this particular guy, or let's take this example for our case. So let's just go ahead and copy this so that we can use this as our reference. Yeah. So we have 1, 2, and 3 as the binary tree over here. And when we come to 2, let's just look at 2 for a second. So when we come at 2, 2 is a leaf. And if it's a leaf, then the left and right are going to be returned as well. They're going to be returned by this base condition, which is going to be equal to 0. So left and right is going to be equal to 0. And you're going to be returning whatever is the maximum that you've encountered so far. So you do max of node val, which is 2, versus 2 plus whatever is the max between left and right. So the same thing sort of goes for one as well. And what that sort of helps us do is we sort of get one path to identify anything. So for a path, you can't really branch off into 1, 2, and 3. By that, what I mean is if I had, let's just say we had something like 4 over here. So we'll take 4, 1, and 3. We can't take 4, 1, and 2. The branching off does not really work out in our favor. So that's the reason why you're returning either the left or the right. I hope that sort of makes sense. But let's just move forward. The main logic sort of resides in how we're using self.max. So after we get the left and the right, what we need to do is we need to update self.max. So self.max is going to be the maximum between self.max, the value that we already have, versus node.val. And what I'm going to do is I'm going to try to get all combinations of node val. So whether it goes on left, right, whether it considers both, I'm going to take all conditions. So I'm going to do node.val plus left, or node.val plus right, or we do sum of all the elements, which is node of left plus right plus the node.val itself. So in essence, what you're doing is you're calculating either the left path or the right path, or consider everything else. Do note that we cannot use the same thing for representing while we're returning it, because inside left and right, you cannot branch off your paths. The path just needs to be either left or right for that case. But when we're calculating self.max, it can contain that triangle representation like this. So that works out in our favor, and that's what we're going to be using as well. And in essence, what's going to happen for us is that if we take this example, let's just go ahead and copy this so that we can do a quick dry run on this. And let's just add this here. Yeah. So you have -10, you have 9, you have 20, you have 15, you have 7. So 15 is, we're just going to go through the traversal. So let's look at the left actually first. So when we encounter 9, 9 is going to have nothing inside its root because it's a leaf, so it's going to return 9 itself. So inside -10, you have left coming as 9. Then the right traversal sort of goes through, which is this guy over here, and you have 20, which is the node which exists. So this return does not really work over here, and it sort of traverses to left and right as well. So you have 15, which is being returned over here. So in essence, when you're at node 20, your left is 15, your right is 7. So then you check for all combinations. You check 20, 15, 20 plus 7, and also 15 plus 20 plus 7, and you compare that with self.max. And the maximum which would have been set in this iteration, or this traversal, this traversal would have been 9. So 9 is less than 42, so 42 is what would have been set. But what you're going to be returning is that you're going to return one path. So the path that you're going to be returning is 20 and 15. So -10 is going to have those values in. So it's going to compare 9 and 35, and it's not going to really conjure up a more maximum value than we've already got. So in essence, it's just going to break out without having to look for anything else, and that's basically the logic. So let's just go ahead and run this, and hopefully this should run fine. And you can see that the answer that we have is the same as our as the expected answer. And let's just go ahead and run this. And you can see that the submission was accepted. And the logic behind this thing was pretty straightforward. You can see it's doing well in the performance state as well, and all the test cases have passed. Um, in essence, what you need to sort of remember when you're doing these sort of problems is that you have this capability of using recursion, and you have this capability of storing the left and the right. It's very common. It's a very common practice to use left and right as your references, but the catch sort of comes over here, where you have a variable which you can reference to build out your logic. So cool. If there was something that you didn't understand, or if you have any doubts, do leave it in the comment section below. I'll try to get back to you as soon as I can. And if you did like this video, do give a like and do subscribe to our channel. We are discussion over here, and we would love to have you on board with us. This was the second last problem of our 30 LeetCode challenge. I look forward to meeting you guys tomorrow. And if you've already subscribed, you're awesome. We all know it, and have an awesome day. Thank you.